Hi guys, my name is Oren Chagai. I'm the CEO of Intelligent RF and Microsolutions. Welcome to our RF Goes Quantum webinar by Dr. Yonatan Cohen, the CTO of Quantum Machines. Yonatan, thank you very much for coming.
All right, thank you, Owen. Okay, so if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. These are the words of Niels Bohr, one of the founding fathers of quantum mechanics, who we see here in this picture together with Albert Einstein, of course. And in fact, for Einstein himself, quantum mechanics was so profoundly shocking that he really had a hard time even just accepting quantum mechanics, this new theory of nature. But shocking as it is, we now know that quantum mechanics is the most precise theory of nature ever invented. So one of the more interesting questions which were asked in the last couple of decades was, can we use this? Can we take advantage of this new quantum world? And can we make it work for us? And more specifically, can we build computers that are based on quantum mechanics? And can these computers perform any better than our regular computers, classical computers? And while the answer to all of these questions seems to be theoretically yes, we know already for a couple of decades that we can theoretically build quantum computers that perform better than classical computers on some tasks at least. It also seems that these days, in recent years, we're also getting quite close. So you might have heard about quantum computing. It's been in the news quite often recently, with many of the tech giants introducing their latest development in the field, their latest quantum processors. And you might have heard about the Google announcement about a year ago that they have demonstrated what's called quantum supremacy. This is the first demonstration that a quantum computer, a real quantum computer, performed some task faster than any other classical computer that we have on Earth. So this happened about a year ago. And this was the first demonstration is not for a useful task yet, but it's a first proof of concept, a first demonstration, and a first big milestone for quantum computing. So this happened with this Google demonstration. So quantum computing is generating a lot of news, a lot of buzz. And the reason, of course, why these computers are so interesting to so many people and so many companies is this great computational power that these computers are expected to bring with them. So the most well-known example for the potential of a quantum computer is the RSA problem. The RSA is the most commonly used encryption protocol on the internet. It's the encryption protocol that we all use to secure our money, our information. Basically, a lot of what we do online is secured by the RSA. And the RSA is based on a very hard mathematical problem. It's based on the fact that it's very difficult for classical computers to break down large numbers into their prime factors. In fact, it would take even a huge supercomputer, a huge classical supercomputer, billions of years to crack even a simple 2048-bit RSA encryption key. A quantum computer could do it in about 1 hour. Okay, so this would have to be a pretty large-scale quantum computer. We're not there yet. We're actually quite far. But it's something which is actually quite imaginable given the great progress of the field in the last decade or so. This computer would be a size of a small room. It wouldn't cost that much. So it's something that we can imagine. So we see that there is a big fundamental difference between quantum computers and classical computers. And this big fundamental difference doesn't lie in the materials that we use to build these devices or the size of the components or the architecture. The big fundamental difference lies really in the very, very basic principles of nature on which these computers are based. So it's in the very basic rules of the game. And so what I want to do in this talk today, I want to first tell you a little bit about these new rules of the game, the rules of quantum computing, quantum mechanics, and how quantum computers can perform better on some computations. And then in the second part of the talk, I want to tell you a little bit about how can we build these quantum computers. And I really want to focus on the role that RF and microwave engineering is playing today, which is a big, big role in quantum computing. So how does RF and microwave engineering is shaping the future of quantum today? And if I have time at the very end of the talk, I want to tell you a little bit about what we do at Quantum Machines. So Quantum Machines so at Quantum Machines, I'm the CTO and one of the 3 co-founders. And at Quantum Machines, we're developing control and operation systems for quantum computers. These are systems that use RF signals to control quantum devices. And so this is actually also how we know Intelligent and how we met Owen. So we came to this beautiful place about 2.5 years ago, looking for some spectrum analyzers. So obviously, this is where you go to look for spectrum analyzers. And we went up to these nice offices right here, where Intelligent is. We met Owen. And we immediately connected with Owen. And in fact, by the end of that meeting, we already got a little room at Intelligent, and we spent 6 months here in this nice place and became part of the Intelligent family. So we really owe Owen a lot for that, and I'm very happy to be here today and give this talk. All right, so. Before we talk about quantum computers and how they work, we should remind ourselves quickly how do classical computers work. So classical computers have 2 main building blocks. We have the bits. This is how we store information on a classical computer. So a bit is just a system that has 2 states, 0 and 1. And so we can implement a bit, for example, in the computer. We have many tiny wires, and each wire can be at either 0 volts or 5 volts or any other voltage that you choose. And this is how we can implement bits on the computer. And this is how we store information on the computer. And then we have the gates. This is the second building block of the computer. And this is how we process information. So a gate is a device that takes some input bits and performs some function on them. This is, for example, the example of the NAND gate. And then we have the notion of a universal gate. So the NAND gate is actually a universal gate. And this means that with a bunch of NAND gates, we can take a bunch of bits, and we can, with a bunch of NAND gates, make them go from any one of their states to any other one of their states at any point in time, according to some program, according to how we wire these NAND gates. And this is really a computer. A computer is just a system that has many states, all the different combinations of zeros and ones of the different bits. And it just goes from one state to another at every clock cycle until it reaches some final state, which is the result of some meaningful calculation, a result of some problem that we want to solve. So quantum computers replace this notion of the classical bit, which can be either 0 or 1 at every point in time, with the notion of the quantum bit or the qubit, which can be both 0 and 1 at the same time. And in fact, it's not that it can just be either 0 or 1. It can be, it's not that it can be both 0 and 1. It can actually be in any combination of 0 and 1. We write it like this: alpha 0 times the 0 state plus alpha 1 times the 1 state. Okay, and these alphas, these coefficients, they are called the amplitudes. And they're actually complex numbers. This is perhaps the most important thing in quantum mechanics. It's a little bit weird, but this is. Let me go back. No. But this is how quantum mechanics works. So we have these alphas, these coefficients of what we call these superposition states, this superposition of 0 and 1, and these are the coefficients. And these coefficients are complex numbers. We can also write these superposition states as these little two-dimensional vectors, and then we have this rule that these vectors must be normalized. All right, there is another very nice way to visualize these qubits, and this is in terms of a vector on a sphere. So imagine that you have a three-dimensional sphere, and then the qubit state is just a vector that points on the surface of the sphere somewhere. This is actually a very accurate mathematical description of a qubit. And so then we can see how the qubit is really just a generalization of the bit. So the bit can be just either 0 or 1, south pole or north pole, but the qubit can be anywhere on the surface of the sphere. Okay, and just like in classical computers, we had the gates to process classical information. So during quantum computing, we have the quantum gates, which is how we process quantum information. So a gate takes in some superposition state and manipulates it, transforms it to another superposition state. So these gates are described by matrices or unitary matrices. These are just matrices that preserve the norm keep the norm of the vector, keep these vectors normalized. So this is, for instance, an example of the Hadamard gate. This is the matrix that represents it. It's a very famous single qubit gate in quantum computing. And then we also have 2 qubit gates, which are described by 4x4 matrices. So these will transform a 2-qubit system, which is described by this 4-dimensional vector, to another state of this 4-dimensional vector. This is an example of the C0 gate, which is, again, a very important vector, a very important gate in quantum computing. I just wanted to go back for a second here and show you that there is also a nice way to visualize these gates in terms of this vector on the surface of the sphere, because when you think about it, at least for single qubit gates, these gates just rotate the vector on the surface of the sphere, okay? So every one of these matrices, these single qubit gates, can be mapped to a rotation of the vector on the sphere, okay? So this will be important later on to get some intuition. All right. And then again, we have this notion of a universal set of gates. Okay, so this means that with only 4 gates, actually 3 single qubit gates and one single 2-qubit gate, we can take any number of quantum bits, which is described by this very long vector of these complex coefficients, and transform it to any other quantum state using only these 4 gates. And that's how we can build a quantum computer. So a quantum computer is a machine that goes from any superposition of state to any superposition of state at any point in time. Okay, so while the classical computer is limited, it just walks along a single computational path here from one single classical state to another and to another, the quantum computer can sort of scan the entire computational, or these many computational paths in parallel. And this is what we leverage, this quantum parallelism, to gain some advantage in the computation. Okay, now there is actually a big problem with this picture right here. And this is the fact that at the end of the computation, we also end up with all of these states in parallel. We end up with all of the results in parallel, in superposition of results. And we don't want all the results, we want a single result, right? The correct result to a problem. So this gets even worse because when we look at the answer, when we want to measure the quantum computer, in fact, we can only see a single answer. This is called the collapse of the wave function. All of these parallelism collapse, and we see a single answer of the computation. And we don't even have any way in advance to predict which answer we're going to see. We're just randomly going to see one of these answers. Okay, so this doesn't seem too good for quantum computers. But there is actually a very nice, elegant way around this. And so this doesn't work for any problem, but it works for many interesting problems, important problems. And the way to go around this is actually to use interference. So I don't have to tell this audience about interference. If you know about RF and microwave, you definitely know about interference. And here, just like waves interfere with one another to either cancel each other out or amplify one another via destructive or constructive interference, so do quantum paths, parallel quantum paths, can interfere with one another. So for example, these two red paths right here that lead to the first computational result here, they can interfere either destructively or constructively to either cancel the probability to measure this result at the end or amplify the probability. This is how you can see also how it works mathematically with these matrices and vectors. So you see these two elements of the vector interfere constructively to give us the 1 over here, while the same two elements interfere destructively to give us 0 over here, because the phase of this matrix element is opposite to the other matrix element that multiplies the vector. So this also shows why phase is so important in quantum mechanics, why the fact that these numbers are complex numbers and they have not just magnitude but also a direction is very important, because that allows us to engineer the interference and to allow this computational path to interfere constructively or destructively. So you see, designing quantum algorithms is really not that simple. It's not that we can just try all the different paths in parallel and reach the result and just scan the entire computational space. Instead, we really have to design the interference, to engineer the interference in order to cancel out the wrong results to a problem and to amplify the correct results to a problem. Again, it doesn't work in every problem, but there is a list of problems, the list of quantum algorithms that we have now that can solve a list of problems, and we hope that once we have large-scale quantum computers, we can disrupt many fields with this new technology. So from computational chemistry, designing new drugs, better materials, better solar cells, through optimization and machine learning, and all the way to cryptography. All right, cool. So this is how quantum computers work in theory. But now to the even more interesting question of how do we build such a computer? How do we build a quantum computer? All right, so to begin with, we should ask ourselves, how do we make a qubit, right? And in fact, we can start by taking a qubit off the shelf. Nature has actually given us very good qubits in the form of atoms. Okay, so an atom, as you know, has a nucleus inside, and around the nucleus, the positively charged nucleus, we have the electron wandering around. But this is actually a very classical picture of the atom. In reality, we really have in the atom a bunch of quantum mechanical states. Okay, a sequence of these quantum mechanical states. These are the famous orbitals of the atom. And this is actually a general result of quantum mechanics, that whenever we have a system that behaves like a particle in a confining potential, we always get this sequence of quantum mechanical states. So when we have a particle in a confining potential, the energy or the Hamiltonian looks like this. We have a kinetic term that's trying to move the particle around, and then we have a potential term that's trying to confine the particle into the well, right? And classically, whenever we have such a system, we always get oscillations, right? The particle oscillates in the well. But quantum mechanically, when we solve the equations of quantum mechanics, we get this sequence of quantum mechanical states that form a discrete energy spectrum. So we have these states, and they're separated by specific energy gaps. This is what happens in the atom, because the nucleus creates a confining potential to the electron, and we get these orbitals. And we can use two of these orbitals as our 0 and 1 states for the qubit. So we say that if the electron is in the 0 state, in one orbital, then it's in the 0 state. And if the electron is in another orbital, it's in the 1 state. And of course, this electron lives in the quantum world, so it can be in a superposition of 0 and 1. It can be both in this orbital and the other orbital. And very nicely, since these two energy states are separated by a specific energy gap, we can drive transitions using a laser beam, for instance, in order to control this transition, in order to perform the gate operations. But I want to focus on a different leading candidate for a qubit today, which are the microwave regime. So where the energy gap between the two energy states of the qubit is at the microwave regime, and then we can use microwave signals to drive the qubit, to drive the qubit gates. And in fact, there are several types of qubits that are controlled via microwave signals. But I want to even focus on a specific one of those, which is called superconducting qubits. And this is perhaps the leading candidate, the leading qubit candidate today. So in superconducting qubits, we make artificial atoms by engineering microwave circuits. So again, this is a leading qubit today used by many big players like Google and IBM. So how can we make a qubit by engineering a microwave circuit? How can we make an artificial atom? So let's start by looking at a simple resonator, an LC circuit. So this circuit is described by two important parameters, two important quantities, which is the charge on the capacitor and the flux on the inductor. And if we look at the energy of this system, it looks like this. We have a Q squared term from the capacitor and a phi squared term for the inductor. Interestingly, since the charge is proportional to the voltage, which is in turn proportional to the time derivative of the flux, the charge behaves like a kinetic term. It's trying to move the flux around, right? It's like a momentum for the flux. So then the system is actually the equations of the system are exactly like a particle in a potential well, again, where we have this potential, which is proportional to the charge squared in this confining potential for the flux. And so classically, we again get the same thing, and this is the famous oscillations of this resonator. This is the classical oscillations at the resonance frequency, 1 over square root of LC. But quantum mechanically, again, we get a sequence of discrete energy states that are separated by a specific energy gap. And because this specific system is what's called an harmonic oscillator, the potential is parabolic because of the phi square term. Actually, the states are evenly spaced in the energy spectrum. So the energy gap between all of these states is the same, and it's actually proportional to the classical resonance frequency, again, 1 over square root of LC. Okay, so, but usually we don't see quantum resonators, right? We work with LC circuits all the time. We don't see their quantum nature. So why is that? Well, there are two important reasons for that. First, we always have some parasitic resistance that causes dissipation. So if we try to have the system in some quantum mechanical states, it dissipates heat to its environment and decays to different states. And the other problem is temperature. Temperature it creates these random excitations to the system that brings it from one state to another. And these two effects, this dissipation and temperature, makes the system look as if it's classical. So, nature is eventually quantum mechanical, but we see it as if it behaves classically. So one solution for that is to cool down the system to very low temperature. So certain materials, like aluminum, for example, when we cool them down to very low temperature, it becomes superconducting, which means they lose any resistance to electricity. So that means they have no parasitic resistance at all, absolutely no resistance. And so then we get rid of these dissipations to the environment. And also, we cool down the system to very low temperature, so we suppress the excitations from the environment. And then if we put the system in some quantum mechanical state, it will stay there, at least for some time. There is always some dissipation at the end, and there is always some excitations from the environment. So it will stay, but it will stay there for quite some time, and we can work with it in its quantum nature. So this is a device used at IBM to cool down these superconducting circuits. It's called the dilution refrigerator. It goes down to 10 millikelvins, okay? Very close to absolute zero, which is roughly about equivalent to 1 microelectron volt, which is about 200 megahertz in photon energy. So if we take an LC circuit, for example, of 5 gigahertz, 5 gigahertz resonance frequency, and put it in one of these dilution refrigerators, then the excitations from the environment are low enough relative to this energy, and again, there is no dissipation, so we really get a quantum LC circuit, a quantum resonator. Okay, so that's great. That's our first, sort of artificial atom, but it's actually not an artificial atom. It's not good enough to make a qubit. And why is that? Well, this is because of this harmonic nature of this oscillator. Because the energy states are evenly spaced, what happens is if we try to put the system, say, in the 0 state and drive it, let's say, from the environment at the resonance frequency, we're not going to stay in the subspace of 0 and 1. We're going to actually drive it, you know, also to the other transitions, like the second state, the third state, and so on. Okay, and we really want a qubit. We just want to stay in the subspace of this 0, 1 and controllably go between one state to another. So this is not a good qubit. In order to change that, we need to replace the linear inductor here with a nonlinear inductor. And this is a cool device called the Josephson junction that behaves as a nonlinear inductor. This is actually an amazing device, which is really just a simple tunnel junction for superconductors. So we have, for example, two aluminum electrodes separated by some very thin oxide layer. And this Josephson device, this Josephson junction, has a remarkable current phase relation, which is not linear. So typically with a linear inductor, the current is proportional to the flux or the phase. With the Josephson junction, the current is proportional to the sinus of the phase. The rest of the equations are very similar, but then if we look at the final energy that we get from this new circuit here, it looks like this. So again, we have this particle in a confining potential, but now the confining potential is not a harmonic potential, but a cosine potential. So it looks something like that. And then we get slight unharmonicity, and the energy states are no longer evenly separated in the energy spectrum. And so now we really have a qubit. We can connect it to the external environment. We can drive it at the frequency, which is the transition between the 0 and 1 state, and we will stay in the subspace of 0 and 1, and we have our first qubit. This qubit is called a transmon qubit, and again, it's the leading superconducting qubit today. Okay, just to give you some numbers, typically these transmon qubits, the frequency between the 0 and 1 state is between 3 and 6 gigahertz, and the unharmonicity is between 100 and 300 megahertz. All right, so now we have a qubit, and we want to control it. We want to make gates on this qubit, right? This is the second fundamental building block of the quantum computer. We have the qubit. Now we want to make gates on the qubit. So here is the transmon qubit. We forget about the higher energy states, at least to some extent now. We connect it to its environment, and we drive it at the resonance frequency of this qubit, and we perform amplitude and phase modulations on the microwave signal to drive the qubit. These amplitude and phase modulations will create our single qubit gates. So this looks a bit complicated, but actually it's quite intuitive, because if you think about just the amplitude and phase modulations of your microwave signal, the phase will determine the axis of rotation, where you're going to rotate the state of the qubit around in this Bloch sphere representation. And the magnitude, the amplitude of the microwave signal will determine how quickly, what the rate of the rotation, okay? So by doing time-dependent amplitude and phase modulations, we can drive any rotation, any single qubit gate of the qubit. Now, there is a subtlety here which is very important, which is the fact that even if you don't do anything to your qubit, even if you don't drive it, the qubit will always rotate around the sphere at some rate, and that's actually the rate is actually the qubit frequency. Okay, so what you really need to do in order to control this qubit is you first need to get a signal generator, a very good signal generator that rotates at the frequency of the qubit, so that it rotates together with the qubit. The qubit is rotating around the sphere, and the microwave signal is also oscillating at the same rate. And then you can take it away from generator and perform your amplitude and phase modulation and create any single qubit gate. So you forget about both the qubit rotation around the sphere and the microwave oscillations if they match together, and you care only about the IQ modulation here, which is actually the logic gate that you're performing on your qubit. So all the logic of the quantum algorithm eventually comes from this waveform generator. All right. So next thing I wanted to tell you about a little bit is the problem of the noise, because now we can drive the qubit, we can make these qubit gates, and you saw how microwave engineering is playing an important role. But noise is always the problem, as it is with every system, and this is where really complicated microwave engineering today is playing an important role. Because noise is perhaps the biggest problems in scaling up today's quantum computers. So even if we look at a single qubit, yeah, we said that the energy gap depends on the charge on the capacitor and the flux on the inductor, and these things could be noisy, right? We can have some fluctuation in the charge on the capacitor, or we can have some fluctuation in the current or magnetic field through the inductor, and this will create fluctuation in the qubit's frequency. Okay, and we saw that the qubit is rotating around the Bloch sphere at the frequency of the qubit. So what happens when we have this kind of noise in the system is that instead of having the qubit rotating at a fixed frequency, a well-known frequency around the Bloch sphere, we now lose track of the qubit phase, okay? Because we don't know at which rate exactly it's rotating around the sphere, so we're losing track of the phase. And we already said that phase is the most important thing in quantum computing, right? This is how we create this interference, and this is how we can beat classical computers. So we have to keep track of the phase. And there are actually many other kinds of noises. So this what we call phase noise, that you just saw is just one kind of noise, because, for example, we always have some leakage to higher energy states. We cannot really forget about higher energy states, and there's also always some decay to the ground state, because at the end of the day, even though these superconductors really don't have any resistance. At the end of the day, the electromagnetic field is three-dimensional, so you can decay to things that are not superconducting in your environment. So there are many different kinds of noises. And I wanted to tell you about three categories of things that people do in order to fight the noise in these systems. So what are these three categories? So, well, we can create better qubits, we can design better environment, and we can also design better control. So just to give you some examples of things that are done, so to design better qubits, for instance, one thing that people have done is to increase very dramatically the capacitance that is shunting these Josephson junctions. This was a major improvement in the field of superconducting qubits. And when you increase this capacitance, you basically make the qubit much less sensitive to charge noise. This was the leading noise mechanism in these devices. So here you see an example of these transmon qubits, where you see this teeth in the fabrication create this large capacitance. This is right here, by the way, the Josephson junction. And this was a major improvement that led actually to the transmon qubit, which is the good qubits that we have today. Then for designing better environment, we can first do better filtering. Okay, so you can filter the noise very well. Many times people embed these qubits inside resonators, inside cavities, two-dimensional cavities, like in this picture, but sometimes also three-dimensional cavities. So people put these transmon qubits inside three-dimensional cavities to filter the noise. And another thing that people do is that you have to do is to clean very well the oxides from the surfaces in the fabrication, because again, we said that at the end of the day, the electromagnetic field is three-dimensional, so it can decay to some of these oxides. Then to design better control, the first thing that you have to do is you have to get a very good low phase noise microwave generator, because again, the phase noise in your microwave generator is just like the noise that we saw before, where we lose track of the phase of the qubit, because we said that the microwave source has to oscillate together with the qubit. So if we have phase noise in the microwave source, this is just like, again, losing track of the qubit phase. And another thing that you can do is you can design better controls in very sophisticated manners. These are pioneering works in the field of optimal control for quantum, how you can design your waveforms so that the gates that you perform are more optimal and more robust against noise. All right, so in the very short time I have left, I want to tell you a little bit about how we measure these qubits. So for measuring these qubits, we actually do use these linear resonators. The linear resonators turn out to be very good for measuring these qubits. So you can couple to your superconducting qubit a linear resonator, just an LC circuit, again a quantum LC circuit, and then the energy difference between the harmonic oscillator states is going to depend on whether the qubit is in the 0 or 1 state. So if the qubit is in the 0 state, the resonance frequency of this LC circuit is something, and when the qubit is in the 1 state, the resonance frequency changes a bit. So we can make another circuit to probe the resonance frequency of this resonator, and then we can again read the IQ values that we get from probing the resonator, and we can discriminate whether the qubit is in the 0 or 1 state. Okay, so you'd see it's already quite a complicated microwave and RF circuit, and again with low noise, filtering, etc. And this is just for a single qubit. Of course, at the end of the day, you have to make it for many qubits, and there is crosstalks, and there is many other challenges here. So you see all of these lines here in the fridge are microwave lines, and we have quantum limited amplifiers. These are amplifiers that by themselves are based on quantum systems, on these Josephson junctions, in order to amplify the signal coming back from these linear resonators, measuring the qubits so that we can really get a good measurement of the qubit state. So there's a lot of complicated engineering that goes into this. Here you see the refrigerator when it's sealed, and all the microwave lines going to the control system. Okay, and in the very short time that I have left, I will tell you a little bit about what we do in quantum machines. So you saw now that in order to control your quantum device, you need this massive array of both microwave sources as well as waveform generator, and you need also digitizers to measure the signals coming back, and you actually also need feedback. Because if you really, at the end of the day, the ultimate way to deal with the noise is by what's called quantum error correction. So after you exhausted all of the, engineering the environment better, designing better controls, etc., at the end of the day, we would have to do some form of quantum error correction. This means that we measure qubit states, and in real time, we can apply different gates to correct for errors that happen in the quantum processor right here. And all of this needs to be based on different new algorithms that are written every day. So every time you want to run something else on your quantum computer, so this is a complicated system. And what we do at Quantum Machines is we're designing this whole system in a new manner, in a unified manner, where we have dedicated hardware to control the quantum processor and software, where at the heart of this software we have our programming language Qua, and we allow quantum programmers to write down their algorithms, their programs, quantum programs in an intuitive programming language, again, that we call Qua. And we have a compiler that compiles this code into our pulse processor, a unique new kind of processor that sits in our hardware and runs the entire program on the quantum device, including the waveform generation, the waveform acquisition, all of the real-time classical processing and control flow that needs to be done in order to execute these quantum programs. So we call it the quantum orchestration platform because we're really, again, orchestrating all of these elements: waveform generation, waveform acquisition, classical processing, control flow, etc. It allows you to run the most challenging experiments of today and realize the quantum possibilities of tomorrow. So with that, let me thank you, and I'll be happy to take some questions. Okay, so let me see. Okay. So there is a question about phase noise. I think that was there was a question about phase noise last year when I gave a similar talk in Intelligent conference in UK. What is a good phase noise for quantum computing for these superconducting circuits? And I think this even changed a bit since last year because these superconducting qubits are improving every day. And so I would say that today a good phase noise would be for the microwave source at say 5 gigahertz. You saw these for example resonators or transmon qubits are at about 5 gigahertz, 6 gigahertz, something like that. So at about 5 gigahertz, I would say at a 1 kilohertz offset, you would need to be better than minus 130 dB dBc. So that would be a good number. Okay, so I'm quoting it for 1 kilohertz, by the way, because for superconducting qubits, at least, the coherence times today are still lower than 1 millisecond. So you actually care about phase noise, which is at offsets that are higher than 1 kilohertz. But this is changing as superconducting qubits are improving. The coherence times are getting better, okay? And actually phase noise of the control systems become more and more of the problem, okay? So in fact, today it's not still maybe the bottleneck, but I believe that as we improve these qubits, these circuits, then the microwave source noise is going to be more and more important. All right, cool. Let's see. Yeah, so a question about what would be the first application of a quantum computer. So this is a good question. I don't think anybody knows for sure what is the first application that we're going to see from a quantum computer. Many people in the field are betting on quantum chemistry, so computational chemistry. Basically, we can simulate the behavior of some molecules, some interesting molecules, and that is one direction. I'm hopeful that perhaps, maybe not the first application, but sometime in the next 5 to 10 years, we're going to see applications in optimization problems. I think that if we can show any speed up that quantum computers can give us in optimization problems, this is something which is very broad and very much in need today. And I'm hopeful that, that perhaps we'll see something of that nature coming along pretty soon. Okay, so I think the time is really running out here. So if you have any further questions, I'll be happy to, if you contact us either through Intelligent or through our website at Quantum Machines. And I thank you again for joining us.